Okay, so what happens if we put two wires carrying current close to each other? What will happen to the two wires? Let's see first how to analyze what happens when you have one infinite wire. The current in the wire is I2, and then we want to see what's the direction of the magnetic field at point P. So before putting the wire here, I just want to see what the magnetic field looks like at this point. The point P is a distance A, perpendicular distance A away from the line. So how would you get the direction of the magnetic field at point P? Well, the direction of the magnetic field due to any element of current is obtained through the ds cross r hat part. ds is the element of length along the direction of the current. R hat points from the element of current to the point where you want to calculate the magnetic field. And if you take the element of current anywhere along this infinite line, the cross product between the two is always going to be out of the page. So the magnetic field at this point is out of the page. It's denoted by the circle with a dot. That means the magnetic field is coming out of the page. Okay, and the value of the magnetic field we derived before, the magnetic field due to an infinite wire, it turned out to be mu node times the current divided by 2 pi the perpendicular area. So this is the magnetic field due to wire number 2 at this point. We didn't yet put the other wire here. We're going to do that next. Let's bring another wire that has a current I1, and we look at a finite portion of that wire. Of course, a wire can't just start from nowhere. The current can't just start from nowhere and end nowhere. It has to be part of a circuit, but we're only going to focus on what's happening to this part of the wire that's of length L. So if you put this wire with length L and the current I1 is going to the right also, what is the direction of the force on wire 1? Well, now we have a magnetic field, and the magnetic field is out of the page, and this magnetic field is due to wire 2. That's this magnetic field in red, and we have a wire with a current, and we know that when you put a wire with a current in a region with a magnetic field, it will experience a force. What would the direction of the force be? Well, the force is given by I1 L cross B. L is a vector that points from the beginning part of the wire to the end part of the wire in the direction of the current. So this is the L vector. And if you get L crossed into B, the cross product will be actually downwards. So the force on wire 1 is actually pointing down towards wire 2. So it's an attractive force. That was the direction. What about the magnitude? This is the force as a vector. The force on wire 1, you put the current in wire 1 times L vector of wire 1 crossed into the magnetic field at the location of wire 1. But the magnetic field at the location of wire 1 is due to wire 2. So that's why it's B2. So what's the magnitude of the force? The magnitude of the force is I1, the magnitude of L, the magnitude of B2, times sine of the angle between them. What's the angle between the L vector and the magnetic field vector, which is perpendicular to the page, coming out of the board? So the angle is 90 degrees. Sine 90 is just 1, so you just get I1 L B2. But B2, we know what it is. It's mu node I2 over 2 pi A. So this is the force then on wire 1 due to wire 2. We can summarize it in the box like that. The force on this portion of wire 1 that has a length L is given by this value, mu node I1 I2 times L over 2 pi A. Okay, what if you reverse the direction of the current in the lower wire? What if it goes to the left instead of to the right? What will change? Well, what will change is the direction of the magnetic field that this wire produces at the location of wire 1. Instead of the magnetic field being out of the page, it will be into the page. Try and convince yourself that by looking at elements of length, elements of current on the wire, and seeing ds cross r hat, and you can show that when you get ds, which points to the left, crossed into r hat, it will be into the page. So if the magnetic field is into the page and the force direction is given by IL cross B, now when you get L cross B, it's upwards. So the force is now repulsive. The two wires repel each other. So when the currents are opposite, the wires repel each other. When the currents were in the same direction, the wires attracted. This is kind of a summary of what we just showed, that if you have two wires that are parallel wires, and they have currents in the same direction, the force is attractive. And if you look from the end view, if I look from over here looking down, so here I see the current coming out towards me, it's perpendicular to the board, and here it's coming towards me perpendicular to the board, the current is in the same direction, then the force will be, as shown, it's attractive. The two wires attract each other. And if in the case where the two currents are opposite each other, then the force is repulsive. And if you look at the problem from this side, look to the left, see that one current is coming out of the page, one current is going into the page, so they're opposite in direction, the currents, and then in that case the forces are repulsive.